Okay. Just finished. Hopefully, you have finished the lecture and the module on, or part of the stuff on refrigerant pressures, temperatures, using your gauges, how systems should work, uh, the different components of the system, those things at this point. So if you haven't done those, go back and watch those. Go back and finish those modules because this is going to build on that. Um, so our refrigeration circuit, uh, we we kind of already. Let me make sure I'm sharing here. Okay. Yep. So we kind of already talked about a little bit about this. That it boils, that refrigerant goes through process of boiling or becoming vapor, evaporating or condensing, becoming liquid. So there's a couple of different terms here that I'm gonna throw out there. These are, in my opinion, probably some of the most important things that you'll use for just proper system diagnosis or proper system performance and diagnosis. So, superheat and subcooling. These are two that you'll hear me talk about a lot. These are those defining factors that um, honestly are a lot of times more important or as important as using your gauges to read pressures, temperatures, measuring temperature inside of a house. This is another one of those important readings that you're going to want. So you need to know how to take it. It's one of those things that I think a lot of people complicate too much. They overcomplicate it and think that it's something that they don't always have to check. And the reason why they don't always want to check it is because they don't really know how to check it, or if they know how to check it, they don't know what that number means once they get it. A lot of people know like superheat and subcooling should be within a certain range. So superheat is a measurement of temperature. It's a degree measurement, so it should be usually between 8 and 12 ish degrees. It can be more, it can be less, depending on circumstances, and sometimes that's fine. But that's kind of your normal rule of thumb range. And so a lot of people can get it to the point where they can maybe even read it. They can say that I have 8 degrees of superheat, or maybe they say I have 20 degrees of superheat, and they don't know what that means or what to do with that number. So hopefully, by the end of this lecture, you'll know how to deal with superheat and subcooling. They're very similar. They're opposite sides of the system, but they're basically the same thing um, as far as how they work. So superheat can be used as a charging method depending on the type of metering device you have. We'll talk about that in future modules, but for now, just let's just assume that uh, at this point, let's just assume system's working fine. Let's not worry about anything being broke or nothing like that. So how does an evaporator work? What's the purpose of an evaporator? So if you go back to the handout that you had from last lecture, we go through our basic refrigeration circuit and we get to the evaporator. And if you go on down here to this picture, this is probably the best one. This is kind of a wider version of the one we're going to look at. So you'll notice as liquid refrigerant comes into the TXV or comes in through that expansion valve or metering device, and it gets broke down into a mist, right? It enters that system as a mist and it has to leave as a vapor. So in order to ensure that it's 100% vapor, we put in a little bit of a security or safety band or insurance policy, as I like to say it, that you have you have proof that you're at 100% vapor, and then you're a little beyond that. So remember, as we've talked before, if you could think back, and I don't have it pulled up right now, but um, that graph of latent, sensible, latent, sensible, the looks like stair steps almost, where you can't be sensibly changing if you're latent changing, which means you can't be changing the temperature of something if you're changing the state of something, and you can't be changing the state of something if you're still changing the temperature of it. So um, if I get something to its boiling point and I keep adding heat, it's not going to raise in temperature. It's going to now raise, it's going to still absorb heat, but that heat is going to be absorbed to change its state until it is completely 100% evaporated. And then, if I were able to keep heating it and contain that in a system, in a vessel of some sort, then I would pressurize that, and that steam, for example, would be what we would call superheated. So once water is heated beyond its boiling point to the point that it becomes 100% vapor, and it then gets heated. If we heated that steam up and we could capture it, we heated it beyond its boiling point. Once it became 100% vapor, all the water was gone. That steam could become superheated. So refrigerant does the same thing. So you'll notice in this picture, in this little graphic here, it's a pretty good little breakdown. You've got your liquid vapor mix. You've got about a 75-25 split. Um, as a general idea of how much liquid to vapor there is coming in. So once it goes through that metering device, it's breaking down, it's flashing off, and it is a 75-25% liquid vapor mix. And then it is working its way through the coils, and because it's picking up heat from the system, air is blowing across from the house, removing heat. Heat's getting transferred into the colder coil. That coil is 30 to 35 degrees below return air temp, and it's also going through the process of evaporating. As a result of that, that refrigerant will evaporate. So it evaporates because it picks up heat, not just because it's an evaporator, right? So it picks up heat until it becomes 100% vapor. Once it becomes 100% vapor, the latent change is over. So up until then, your pressures and temperatures really probably didn't change a lot inside this coil, um, and they're not going to change a whole lot after this. In this evaporator, your pressures are not going to change that widely, but your state is going to completely change. So once it becomes 100% liquid, or 100% vapor, every degree of heat, every BTU, every ounce of heat that's put into that coil, into that refrigerant, is going to be absorbed in the form of superheat. So superheat is additional sensible heat added beyond the point of complete evaporation, or beyond the saturation point. So a saturation point is anywhere where you have liquid, or you have liquid and vapor mixing, for example. Either it's going from vapor to liquid in the case of condensing, or it's going from a liquid, or from a liquid to a vapor in the case of evaporating. I may have said that backwards, but you get the point. It becomes 100% vapor, and then we add more heat, which is called superheat. So this little graphic, it shows that your saturation temp at complete saturation is 40 degrees. So remember I said in the last video that your saturation temp will be 30 to 35 degrees below indoor temp in your evaporator coil. So if that's 40 degrees, let's say it's 70 to 75 degrees in the house, you got a 40-degree coil. That's pretty common. So a 40-degree coil, once that becomes 100% liquid, 100% vapor, and the liquid is all gone, it starts to go through a sensible change. That 40 degrees is what your gauges are going to read. So remember I said I don't really care about pressure. It doesn't matter what the pressure is, because pressure is a byproduct of temperature. But the temperature, if it's 40 degrees, it's reading it right here. So when I put my gauges on and I say, what is your evaporator coil temp? The saturation temp is what I'm talking about, and that's what this is pointing to. Um, Beyond that, your pressures don't change. Your temperature of the refrigerant doesn't change. The saturation temperature of the refrigerant does not change, because that's what the gauges are reading, or the saturation point. Beyond that, everything we add is sensible, or superheat. So superheat does not follow a PT chart. So if I add 10 more degrees, you're not going to see that reflected on your gauges, because the gauges are reading saturation. I know that's confusing. I know it's hard to understand. It's hard for me to understand, but that's just kind of one of those things you just got to take for what it is and move on. Um, so how much superheat should we have? How much additional heat should we have? Is more better? If I got some, why not have more? So why do we have it in the first place? Well, a few different reasons, but one of the reasons is it ensures that there's no danger of liquid. The main reason is that there's no danger of liquid getting back to the compressor. So if we get liquid back, we've already talked about how that can damage the system. So we don't want that to happen. So we kind of give it a little bit of a deadband there, or a insurance there, that you've got this so many degrees of insurance there of sensible heat before you get liquid coming back. So you don't want this coil completely, full of liquid, or even to the point that it's evaporating and all the liquid isn't gone before it leaves the evaporator. That's where you start getting into damaging your system. So why not have 100 degrees of superheat, or 50, or 20, or how much is too much, how much is not enough? Well, we'll learn how to do what we call target superheat later on, but for now, if you kind of stay in the 8 to 14 degree range, that's a good range. That's not going to be perfect in every condition, but it will get you close. Um, so if you figure 1 to 8 to 14 degrees, I don't think you'd mess it up too bad. Uh, but hopefully we'll learn more beyond that. But at this point, let's just say that we want that superheat to be 8 to 10, 12, 14 degrees at the most. So what does that mean? Well, that means I'm adding about that many degrees of sensible heat to the refrigerant after it has completely boiled off or evaporated. All right. So how is that measured? How do we measure superheat? Well, there's a couple of different ways, and I'm trying to see what he's. These are really good pictures here, but and you can go back and watch these videos. This guy's really awesome. He's got a lot of cool stuff in here. So there's your flash gas. He says 80, 20, 75, 25, whatever. Trying to see if there's a better picture of it. All right, so I mentioned earlier that your saturation temps aren't going to change during the part where it's changing states. This is kind of proof of that. If you could measure pressure entering, which you really can't, entering the evaporator and leaving the evaporator or at the saturation point, it would be the same. So that whole low side is going to be under the same amount of pressure, same as the high side. Pretty much is going to be under the same amount of pressure. So this 14 degrees extra of superheat, you don't see that on your gauges. That is sensible heat, not latent. So your saturation temp is measuring kind of the latent. I know it's confusing. All right, so how do we measure that? Well, here's a good picture right here. So let's use this. So you got your coil, you got your outdoor unit, your indoor unit. Here's the way that we're typically going to measure it. This is just the way a service tech's usually going to do it. He's going to do all of his readings outside where he's got his gauges. He's got his little valves out there that he's going to put his gauges on, his hoses on. He's going to use that to measure pressure and convert that pressure to a temp. That temperature is going to be saturation temp. So in this case, saturation temp is 40 degrees. And this will be a little extra research for you, if it's 40 degrees and the system's running 410A refrigerant, what pressure would it be under? So there's a little assignment for you to look up. So what would be the pressure at 40 degrees? All right, so I'm not going to tell you. You can figure it out. All right, so excuse me. At 40 degrees, we add additional heat beyond saturation, and in this case, they're saying that it's 55 degrees. Okay, what does that mean? Well, that doesn't mean the refrigerant is 55 degrees warmer. That means the line itself. So the way we measure that is we actually, and I don't know if I've got a picture of that pulled up, but you actually clamp some sort of a probe, or um, even a thermometer will work if you have to, a little probe type thermometer. Insulate that as best you can so it's not getting measurements from outside air, and you're measuring the temperature of that line. Well, why do we measure the temperature of the line when I told you earlier that if I ask you how cold the coil was, you wouldn't measure the temperature of the coil? Well, when I say what is your evaporator temp or your coil temp, I'm talking about saturation point, saturation temp. But when we measure superheat, because superheat is sensible, because it's beyond the saturation point, it can be measured with a thermometer. So the easiest way to do that, because we can't just stick it inside of the system, is to measure the copper line. So we try to measure that as accurately as we can. That reading minus the saturation temp. So remember, superheat is just sensible heat. 1, 2, 3, 4, 5, 6, 7. Right? Just counting, degrees of change beyond saturation. We take the line temp minus what our gauges told us. That tells us what our superheat is. So without getting too involved with what exactly that means or how we use that to diagnose, that's how you measure it. So here's a good image. So in this case, he's got his gauges here. You've got, looks like 410A refrigerant is in the middle. So if you trace that up, you've got about 30, looks like about 38 degrees, which is about 115, 120 pounds. There's your high side temps. So on your high side, so if it's, we don't know what it is in the house in this picture, but let's assume that it's 70, 72. So we're running a 38-degree coil. That's not horrible, right? Indoor minus 30 to 35. So that's not bad. That looks pretty good actually. And then high side, outdoor plus 20, assuming that it is, and we don't know how warm it is exactly outside, but let's say assuming that it is 80 degrees outside, then you're running outdoor plus 20, you're running 100 degrees. So if you go to the 410A chart, trace that up, you got 100 degrees there. I don't really care what the pressure is, but in this case, it's like 320, 325. So indoor minus 30, outdoor plus 20. Pretty simple. Once you do that a few times, it'll become second nature. So don't freak out if you don't get it yet. Repetition. Now you'll notice over here he's got like a dual temperature clamp. So he's got a high side temperature clamp and a low side. And he's got them clamped on the system. This is the way you'll do it. This is one way you'll do it. They make smart gauges and digital gauges that'll do all this for you. You can get an even simpler system and just get a thermometer, but this is a pretty good setup. If you had some sort of dual temperature probes with clamps on them, you can clamp those on those lines and get a pretty good reading. So the first one is strapped to the liquid line. That's going to be where we measure our subcooling, which we haven't talked about yet. Your superheat is going to be measured on your vapor line or your suction line. So that's the big line, the insulated line. That one should be cold. It should be probably sweating most of the time. And so he's measuring that and saying it's 55 degrees, and your pressures are about 38. So a little different than his example, but pretty close. So you're looking at about a 17 degree, about a 17, 18 degree superheat there. Be a little higher than what I would like, but maybe in this case that's fine. So like I said, there's things that could change that. We're not going to get into all that right now. Different types of metering devices. Go on from that. All right, so in here, he's going to start talking about target superheat, which we're not going to get into yet. And now we're going to talk about subcooling. So if you go to this guy's website, there's a lot of good stuff here. I've actually talked to him a few times. He's a really nice guy. He's a teacher and has worked in the field. So I recommend this site highly. Subcooling is basically the same thing on the other side. So what is your condenser's purpose? Condenser is to reject heat, and as it rejects heat, it gives up its heat in the form of latent change of condensing. So it enters as a hot gas, it starts to lose heat to the air, and eventually becomes 100% liquid. It has to become 100% liquid in order for that metering device to work right. So we have to ensure that we have 100% liquid. So how do we do that? Basically the same way. You measure your high side temperature. So remember, there's a good picture. Earlier I said that your discharge can get really warm. There's a good example of that. So in this case, this one's 170 degrees. And then your saturation temp is 105, and your liquid line temperature is 93. So what is your subcooling? Well, let's see if we can get a little better look at that. Okay, so you put your gauges on like so. You read 100 degrees, 100, yeah, let's say 100 in this example, and you've got 95 degrees on your liquid line. So what is your subcooling? It's the same thing we did with superheat. It's it's backwards. In superheat, your refrigerant temperature would be lower than your line temp. Your line will always be warmer because it's superheated, right? So it's beyond saturation. It's additional heat added. In the case of subcooling, it's actually additional heat removed beyond saturation. So beyond 100% liquid, you got additional heat removed. Um, so if he's using 100 degrees in this example on his gauges and 95 here, your subcooling is 5 degrees. That's how you'd measure that. There's a good picture of a TXV, kind of a funky looking thing, but pretty common. See those a lot. And that pretty much sums up superheat subcooling in a nutshell. I know it's not going to be real clear to you yet, but hopefully that gives you a good idea how to do it. So when you come into lab, you should have an idea of the things you're going to need in order to measure superheat. What do you need? Uh, you need gauges. You need a PT chart, but you have that on your gauges. You need a thermometer of some sort of temperature probes. So clamps would be great, so you can measure temperature, and that's it. I'll tell you a little story here, and then we'll close this lecture out. I had a guy one time that was trying to diagnose a system, and he was asking me what his pressure should be or something. And so I was telling him, well, your saturation temperature should be this. And he's like, well, man, we can't get this thing to work like it's supposed to, and we keep messing with it, and it's not working like it needs to work. And I said, well, what's your superheat? And he's like, man, I tell you, we could measure all that. We could measure superheat. We could go and take all those readings. But he said, oh, that's just too much trouble. We're not getting paid enough to do all that. And he's like, it's just a big task. And I said, you give me a thermometer and you give me your gauges, and I'll show you how to measure superheat. You can measure superheat, and you already got your gauges. If you already got your gauges on anyway, you can measure it in a minute. Now, learning to interpret that data takes a little bit more practice, but once you understand the theory of it and what it's doing and how different things in the system affect it, uh, it's a really good tool to tell you, where where you need to add a little refrigerant, or where you may have an air restriction, or where you may have a refrigerant restriction. So without superheat and subcooling and understanding how they work, and then understanding how to apply those to troubleshooting, it's really hard to just go in and diagnose everything on a system, because you just can't do it. Um, you might be able to get by and you might be able to fake it, but you don't really understand. If you don't understand what it's doing or why it's doing it, it's really hard to fix it. So um, that will get you started on your superheat subcooling lab work. So if you have any questions on that, be glad to answer those in class. But that should pretty much wrap that up.